So how do we know when we're out there in the real world what type of model to use? We've talked about different models: linear models, exponential, logarithmic models, logistic growth model. And what do those look like? Well, a linear model is going to be something like y equals ax plus, mx plus b. I'll just use our formula. And that's going to be a straight line, right? Okay, an exponential model, if it's a growth, it's going to be going like this. If it's a decay, it's going to be going like that, right? So exponential growth or decay, something like that. And those models look like, so we've been working with those quite a bit today. A logarithmic model, we haven't really seen that, I don't think. We've done the graphs of logarithms, but like in this 6.7, I don't think we've had that kind of model. But it's going to be going something like that, where it's kind of curving that way. And so it might look like something like y equals a natural log b. Something like that for a logarithmic curve. And, the logistic model. So logistic would look something like it's growing, it's starting somewhere and it's growing, and then it's starting to taper off. So it would look something like that. And we had the logistic model. I won't put that up there. But anyway, so that's what you're looking for with these pictures. Well, how do you get the picture? How do you get the graph? They have to give you data, or you have to go out and get the data yourself. Now that takes a lot of time and a lot of data to get a good model. But here they just give us a little bit of data. They give us a little table of values, and we're going to plot that and see what it looks like. So I'm going to be counting on my scale, 1, 2, 3, just like that. That's going to be my x. And then my y is going to be, I'm going to count by 2 lines being a 1, a 2, 3, a 4. Because you can see it, the largest I'm going to get is 4.39. You can look in here and see if anything else is larger, but no. So I'm going to graph this based on my scale here. I don't even know where this data came from. I don't know what x is representing or what y is representing, but I can graph the ordered pairs. So 1, 0, that would be like right there. 2, and then it's over 1. It's like almost 1.5, so it's going to be like maybe there. 3 is going to be just above 2, so there. 4 is going to be 2.8 about, so 2.8 maybe there. 5 is 3.2, so there. 6 is just above the 3.5 mark. Oops. That always happens. 7, getting closer to 4 there. And then 8 was just over 4. And 9 is about there, 4.3, 4.4. So those are the ordered pairs that we have. That's the data we have. It is not a straight line. So there goes the linear idea. It's not linear. It looks like it's going like this. Okay. So it kind of looks like a logarithmic curve. So we're going to go with a logarithmic. It's a logarithmic model. And so y equals a natural log of b. Now we can find a and b. We know some information. First of all, we know that it's 1, 0. So if I'm putting in 0 for y, so I know this ordered pair. I know a couple ordered pairs. I know 9 ordered pairs, right? 1, 0. Okay, so remember this is my x, this is my y. I forgot to put x in the model. That's what's thrown me there. Okay, so natural log bx. Squeeze that in there. I'm getting an output of 0 equals a natural log 1x. Okay, I'm sorry, that's supposed to be a b. X was 1. I'm trying to find b. B times 1. Okay, so 0 is equal to a natural log b. Now, this is multiplication, so you actually have two choices. A could be 0. Well, that's not very likely, because if a is 0, then the whole thing is just 0, and it's going to be a horizontal line. All your outputs would be 0. So we're going to not do that one. And so we're going to say, when is the natural log of b? When does that equal 0? Well, you can think about, okay, e to the 0 equals b, and e to the 0 is 1. So now we know what b is. B is 1. We're trying to get this model. We're trying to find a and b. Okay, so now I'm going to use another point, and I'm going to use this point at the end, and it's going to be 9 for x and 4.394 for y. So we're going to say 4.394 equals a, which we know is 1, right? No, a we don't know. That's what we're trying to find. Natural log b is 1, x. That's our formula so far. Now, I should have put a y there. I'm going to fix that. Y equals that. Okay. Now, we can say, use this point here, 4.394 equals a natural log of 9. Well, that's what we want to do. We want to solve for a. So it's going to be 4.394 divided by the natural log of 9. That's going to equal a. So now I have a formula, a model with a formula here that's going to say y equals, and then my a is 4.394 divided by the natural log of 9. And then I'm going to have the natural log of x. Okay, so this is a good model. I would probably use that for my model if I were doing this. You could get a decimal approximation for that. So just on your calculator, you'd go 4.394 divided by the natural log of 9. And it turns out to be, looks like it's about 2. So that's approximately 2. So if you wanted to use that approximation, you could say it's approximately 2 natural log of x. Remember that b was 1. Okay, so either way. I kind of like using this because we've been working with things like that and it's a little more accurate.